Hey everyone, in this video I'll talk about the least squares problem, or linear regression, or the line of best fit. Let's take a look at the 6 points A, B, C, D, E, F on the Cartesian plane. Apparently that these 6 points do not form a perfect line, but they do follow a positive linear relationship. The question is, can we find a line that best fits all of these points? Well, we can try to come up with a million different lines, but can we find the one line that would mostly fit all of the points? Let's start with the equations, linear equations, y equals mx plus b. Imagine that the 6 points fit one linear equation. That means we can come up with a system of equations whose x values here are the x coordinates of each of the points. The y values are the y coordinates of each of the points. From the system of equation, we can transform it into a matrix equation. A is a coefficient matrix, x is a variable vector representing the values of n and b, y is the y values of all of the points. This is an overdetermined system, and most of the times, this kind of system are inconsistent. So we can't find a solution for this equation, which makes sense because we can't find a line that fits all of the 6 points. The good news is, if we can find projections of y onto the column space of A, then the new equation ax hat equal to y projections will be consistent. So we have to find projections of y onto the column space of A. Does that projection vector exist? If it exists, is it unique, or there's many of them out there? The theorem number 1 will show the existence of vector projections. So if you're looking at a subspace S of Rm, for each of the vector in Rm, you can find a unique vector element P in S that is closest to B, which means the distance between B and P is the closest distance between B and the subspace S. Imagine this is a subspace S, this is a vector B, you can find vector P on S such that the distance between B and P is the smallest. Connecting this theorem to the equations, in the original equations, vector B is the original y values vector. The subspace is the column space of A, and vector P, the projections, is the projection of y onto the column space of A. So now a vector projection exists, and it is also unique. So if a matrix A, n by n matrix of rank n, which means all the column vectors of A are independent, then the normal equations A transpose AX equals to A transpose B have a unique solution. And the x hat, the unique least square solutions, is the least square solution of the system AX equals to B, and it is the solutions to the new system where B is the projections onto the column space of A. Well, let's look at the 6 points. This table shows the xy coordinate of the 6 points, also the representation vectors of each of the points in R squared. So we wish to find a linear equation with a line of best fit. I call it y hat equals to mx plus b. I use y hat because I want to distinguish between the y that you find using the line of best fit and the y value, the real y value. And we call y hat as a fitted y. So the problem is to minimize the difference between the fitted y and the real y. Okay, so the difference is the y hat sub I is the y value that you can calculate it using the line of best fit, using x sub y. Y sub I is the real value of y given x sub I. And here x here is just the given value of x. So the difference between the fitted y and the real value of y is called the residual. And if you can minimize the residual square, then that is the target, that is the objective of the problem, is minimizing the square of the residuals. From that objective, the name least squares is where it's come from. Looking at the graph, especially at point B, if you project point B onto the y-axis, you get the real value of y. If you map point B onto the line of best fit, the orange line, and project it over the y-axis, you get the fitted value of y. And the green vector is a residual of B. So each of the point has its own residual, and minimizing the residual square is the goal of the problem. Now going back to the system of equations and using the matrix of equation, and you plug in x and y value of the 6 points to get a matrix equation to solve for m and b, which is the slope and the y-intercept of the line of best fit. Using the equation ax equals to b and the theorems of existence of uniques of a vector projections, we can find the least square solution x hat, which is plugging in A transpose A. Take the inverse of the product, multiply by A transpose, multiply by y, you get the vector mb. And using the value of m and b, you can create the line of best fit for the 6 points. Right. So the orange line here is a line of best fit of these 6 points. But the question is, why do we want to find the line of best fit? Well, if you only have 6 points as a data point, and then once you can find the line of best fit, you can use this line in order to estimate the y value of points whose x values are not one of these points, one of the historical data points. For example, what if I want to find the y value when x equals to a? Well, I start at the x-axis, go to the line, and this is the g, I call it point g, right? In order to find the y value of this point g, I just need to plug x equals to a into the line of best fit that I found earlier to find the y value of g. And again, this is an estimated value, not the real value of g, not the real value of a point whose x value equals to 8. Similarly, if you want to find the y value when x equals to 10, you don't have historical points for x equals to 10, so you should use the line of best fit to estimate a y value for this point. I call it h. Just plug 10 into the x. You can find the y value. Alright, so this video shows an introduction of the least squares problem from the linear algebra points of view. And it shows you how to use matrix equations and the least square solutions in order to find the line of best fit for a set of data sets in Cartesian plane. Well, I hope you learned something new today.